So we are dealing with the fourth problem in this collision series, and the fourth problem in the collision series is problem number 1.168, and the problem is stating a particle of mass m1 experience a perfectly elastic collision with a stationary particle of mass m2. What fraction of the kinetic energy does the striking particle lose if it recoils at right angle to its original motion direction, and in the second part the collision is a head-on one. So let us approach this problem by understanding it by drawing the situation diagrammatically. So this is the situation which is described in the first part, where the particle m1 moving with a speed u is colliding with a stationary particle m2, and post collision m1 is recoiling at a velocity v1 which is perpendicular to its initial direction of motion, and over here we have considered that m2 will be moving with a velocity vx in the x-axis direction and vy in the y-axis direction after collision. So the first thing that we do is we apply momentum conservation in both x and y direction. So we apply momentum conservation, that is the particle is said to be conserving momentum in the x direction and the y direction. So the first thing that we do is we are applying momentum conservation in the x direction. So m1u is equal to m2vx. So vx equals m1u by m2. This is equation A. Now the next thing that we do is we apply momentum conservation in the y direction. So P initial in the y direction is equal to P final in the y direction. So along y. So in this initial situation there is no y component of velocity. So initially it is 0. And in the final situation m1 v1 is in the upward direction positive minus m2 vy, and from here we obtain vy as m1 v1 divided by m2, and this will become b part of the problem. So over here we can say that the particle 2 will attain a velocity v2 in this form m1u upon m2 I cap minus of m1 v1 upon m2 j cap. The negative sign represents that the velocity of the particle 2 is in the downward direction, that is in the opposite direction in the y-axis. So this is v2. Now the next thing that we consider over here is, since the collision is perfectly elastic in nature, so if the collision is perfectly elastic in nature, then we can say that the kinetic energy is conserved. So since collision is perfectly elastic in nature, then we can say the kinetic energy initial is equal to kinetic energy final. So over here if we use this expression, then we can say that initially the kinetic energy is possessed by half m1u square, and finally it is in terms of half m1. So over here this particle is having velocity v1, so v1 square plus half m2 and then v2 square. So v2 square we can write it as the magnitude of this term, so m1 square u square upon m2 square plus m1 square v1 square by m2 square. So we have an expression like this, and from here we express a relation between v1 square and u square. So v1 square and u square, so we write it as v1 square by u square equals m2 minus m1 divided by m1 plus m2 or m2 plus m1. So this is what we obtain when we equate the kinetic energies. Now the problem is asking us what fraction of the kinetic energies does the striking particle lose. So kinetic energy fraction of kinetic energy lost by striking particle. So kinetic energy lost by striking particle. So we calculate the loss in kinetic energy by the original kinetic energy. So loss can be written as half m1 u square minus half m1 v1 square upon initial kinetic energy, that is half m1 u square. So if we solve this, we get half minus half of m1 cancel, v1 square by u square. So we have already deduced this expression v1 square by u square, and hence if we subtract 1 minus m2 upon m1 plus m2. So if we solve this expression, we get that delta kinetic energy is equal to twice m1 upon m1 plus m2. So this is the solution to the first part of this problem. Now let us deal with the second part. So now in the second part, we are considering the situation like this, where the collision is said to be head-on in nature. So if the collision is head-on, then we need to apply momentum conservation only in the direction of motion, that is in the x direction in this case. So if we apply momentum conservation, then we can say m1u equals m1v1 plus m2v2, and this will serve as equation 1 for B part. And in the second part, we say that we can apply kinetic energy conservation. So kinetic energy initial equals kinetic energy final. So over here we can say half m1 u square equals half m1 v1 square plus half m2 v2 square, and this will serve as the second part of the problem. We can also use the coefficient of restitution formula to get the required result. And on here we get on solving that v1 equals m1 minus m2 upon m1 plus m2u, and v2 equals 2 m1u upon m1 plus m2. So we'll get something like this on solving this expression. This is most of the time a solved case in the classroom also. So over here we need to find the change in kinetic energy, or the fraction of kinetic energy lost by the striking particle. So the kinetic energy fraction lost by a striking particle, so we write it as half m1 v1 square minus half m1 u square upon original, that is half m1 u square. So over here on solving, we obtain v1 square by u square minus 1, and v1 square by u square can be evaluated from this expression that we have. So v1 square by u square minus 1. So over here we can write this as m1 minus m2 upon m1 plus m2 squared minus 1. And on solving, we obtain this expression. So here we obtain minus 4 times of m1 m2 upon m1 plus m2 squared. Now since we are only evaluating the magnitude part, so over here if we calculate the magnitude of kinetic energy fraction, So we can write the answer as 4 m1 m2 upon m1 plus m2 squared. So this is the final answer for the problem 1.168.